All right. Hello, everyone. Welcome to Haunted Physics Lab. Welcome to Haunted Physics Lab. This thing is blocking a lot of sound. I am the president, Joshua Lewis, and today, welcome to our spooky physics. You're going to be seeing a lot of really fun demos and even more fun science. I'm going to introduce Alex.
Hey, I'm Alex. I am your vice president of InReach, and basically I just coordinate fun activities such as this. Although this activity was coordinated by Austin here.
Hello, I'm Austin. I'm the vice president of Outreach. My job is to basically reach out to the community, set up events like this, and I hope you guys have a lot of fun tonight. Here is our treasurer, Portia.
Hey guys, I'm Portia. I deal with all of our finances here, so I make sure that we have the funding to put on super cool programs like our Haunted Physics Lab. And here is Ashley.
Hi, I'm Ashley. I'm a VP of PR and Communications, which means I just reach out and make sure that all of our social media is up to date, get people excited about physics, and we're all super excited to have you here watching with us. So let's get this show on the road.
Cool. So most of you guys are 5th, 6th, or 7th graders. Hello, welcome. We're going to show you a lot of cool demos. Some of them are a little bit technical, but some of them are also like really intuitive, which means like you can really understand them with basics. So for example, we have this first one. So basically I have this plank and it's hung up by strings. And then I have this cup here and there's a ton of marbles in it. And I'm gonna put the marbles in the cup. So what you might think is, oh, if I like just swing this cup, oh, all the marbles are gonna fall out, right? Well, actually, I can do something special, and you might want to back up for a quick second. So what I can do is I can swing this around in a circle, and if I do a perfect circle, I can make none of the marbles fall out. So remember, there's still a lot of marbles in here. I'm going to swing it. Ready? 1, 2, 3. Wow, none of the marbles came out. That's awesome. So that's physics for you. That's our first demo for tonight. Next, we have some cool things about gravity. Alex is going to show you that over here.
Hey y'all. So basically, what is our universe made of? Well, we don't quite know that yet. But what we do know is that we can think of the universe as this kind of stretchy fabric. Now, essentially what this means is that 100 years ago, there's this guy named Einstein who said, well, the universe is basically stretchy like this. Well, not physically stretchy, but when you have a heavy object, such as a marble right here, it deforms it slightly and it creates an indent. And it's this indent that actually causes this gravitational attraction. So let's see what that actually means. Well, let's say that we have a very heavy object like this, and this is our space right here. Well, if we put it in here, as you can see, it deforms it. But the level of deformity is very strong at the center. So when I have this marble here, it goes very fast into the middle. But if I have a marble out here pretty far away, it goes slower and then fast into the middle. Now, because of this marble right here actually wants to go straight in, but it doesn't really want to change where it goes. It's called inertia. It's resistant to change. So let's say I put this in here at the right speed, it orbits it almost perfectly, but it orbits it in actually ovals, not quite perfect circles. So what else can I show you with this? Well, let's say, why does everything in the solar system orbit in the same direction? Because we don't have any planets that go in reverse. Well, if we start off at the very beginning of the life cycle of the star, we have a whole lot of things going like this. What if we put some things going in the other way, like this? Over time, you get enough collisions like that, and everything goes in the same direction. You don't have anything left over that goes in the opposite direction. So there's a net rotation that prevents anything from going the other way, because if something did go the other way, it would cancel out and get kicked back into the same direction. So what else can I show you with this? Well, what happens if we have a moon, say, that gets too close to its planet? So a moon essentially is, like any body in our solar system, just a bunch of rocks held together by its own gravity, like this. Now notice that if we take this moon here, and we have a very heavy star or a very heavy planet there, and we spin it around on the outside, they stick together at first because of their gravity. But let's say they get too close, as you can see, they get torn apart. And we're now left with rings. Now, what planet in the solar system has rings? Well, Saturn. Now, Saturn once had moons, but now they're rings because the moon's got too close to its gravitational pull and just tore it apart like that. So that's ultimately what we can show with this demo. Now, let's go on to vacuums.
Welcome to vacuums. Now, vacuums are those neat little things that we find that suck up all the dirt in your house. Or it's the thing that we find in space, the thing between celestial objects. So today, I'm going to show you the interesting ideas of vacuums. What? Louder? Oh, okay. So, first, let's show you this. This is an interesting object here. This is what's called a bell chamber. It allows us to create a vacuum here in our own home. So what I'm going to show off first is one of the most famous quotes with vacuums is "No one can hear you scream in space." Meaning that when we have a vacuum, we actually have blocking sound when we have a vacuum. So I will set off this loud, annoying device and put it inside the bell jar. I hope you're still able to hear it lightly. So now I'm going to pull a vacuum on it using this device here. If I can get the seal to work. There it goes. And now we're sitting at a very low pressure, something close to space. And as we take that off, notice how we can barely hear the ringing. It's almost gone completely. And as I let the pressure back in, it's back. Now, I'm going to need a volunteer. Austin, Alex.
Yes.
We are now going to use this interesting device. Now first, volunteer, put this on. Right there. You can put it on with your hands. It's not easy to put on, which is why I wanted you to put it on. It's not easy to put on. Vacuums are a dangerous thing. Only let professionals do it, or you won't be able to do this. Now, I'll take this and I'll close it. And we will go ahead and open the valve, turn this on. We've now created a vacuum inside this object here. Now, I'm going to lock it so that the vacuum stays in, or pull that off. Now, would someone hold the other side of that?
It's not coming off, Josh.
No, it's not. You know, the vacuums inside your home work by sucking up materials. Well, this just sucks on both sides of this until it is almost impossible to even be able to pull it apart. But watch as I let the pressure back in. Voila, it's open just like that. Now we are going to move over to one of my favorite experiments. I need a ping pong ball that I lost.
Thank you very much, Austin.
You'll see, this is just an ordinary hand hair dryer covered in duct tape in its red Solo cup. Now watch as I put the ping pong ball on it. As it floats in midair. Ooh, spooky. I can even turn this and it'll follow it. Our levitator with just plastic cup and hair dryer works. Just like that. Now, we'll move on to other experiments in this direction.
Hey, so one thing I want to show you is what happens when we get a very heavy object and we get it to spin. Well, everything has inertia. Essentially, it doesn't want to slow down, it doesn't want to stop. So even when it's on here spinning, it'll still keep going as it creates noise. Now, as you can see, at first it starts to spin, but nothing really happens because it starts to decay. So even though it wants to keep going, different things like friction and air resistance, they start to slow down. But watch what happens now. As it gets closer, and it keeps doing this more times, it actually starts to generate sound. And sound actually gets higher and higher as it gets closer and closer.
That is really taking a long time, Alex.
There it goes. And you see, it gets louder and louder because it keeps hitting it more and more. And then stops.
Whoa!
So that's conservation of energy for you. But what happens when basically we have something else entirely? What happens if I actually try to insert energy into the system? Well, let's say that I have this right here. What does heat want to do? Heat wants to rise. That's because hot air is less dense than cold air. So if I were to heat this up, as you can see, this is now less dense. As air is trying to push this in, it's pushing this up there like a straw. In fact, we can actually get it to go all the way up. Now my hands aren't that warm because I'm not really that nice of a person. So it might take a little bit to kind of get up. But once it does get up there, as you can see, I basically put the entire amount.
We need a volunteer's warm hands.
Yes, here, Josh is a nice person.
I have
So
really
there we
warm
go.
hands. I've been a nice person.
So is that heat coming from your hands, making it boiling?
Yes, just the heat of my single hand.
Wow.
Look at it go. Look at it boil. Ooh, spooky. Here you are.
There we go. Thank you, Josh. And then if you were to just let it be, it starts to go down. That's because it's cooling down. Now you don't have all that extra energy. The energy is being dissipated. So it stops from being up there and starts to make its way down. All right, now on to Austin. You're going to do some more conservation of energy.
Hi guys. So this is a Newton's cradle. If you guys have ever heard of it before. There are 5 balls here and they're all hung up by strings. So you can see, what if I take this ball and I let go? Oh wow, it's transferring energy between the balls and making them go back and forth. That's crazy. You can see when one of the balls bounces on one side, then the other one does on the other side. What if I stop this and do 2 at the same time? What do you guys think will happen? Well, let's go ahead and see. Wow, this time not only 1 ball bounces on the other side, but 2 at the same time. That's because I pulled up 2 of the balls at the beginning instead of 1, so there's double the amount of energy going into it. That's pretty crazy. That's called a Newton's cradle. And let's show you another cool demonstration involving motion. So you see here I have a very large ramp. This one's very flat, and then I have a very curved ramp. So I have these cans over here. They are very large cans. One has some racing stripes on it, and one has some polka dots on it. So what I'm going to do is I'm going to drop them both at the top at the same time. Which one do you think is going to hit the ground first? Is it going to be the polka dot on the curved ramp, or is it going to be the flames on the flat ramp? Let's go ahead and see. 3, 2, 1. Which one was it? The polka dot one. Now, does anybody know why that's the case? Why would the polka dot one go down first? Is it because it's polka dots and this one's flames? And the flames somehow slow it down? Let's check again. Let's try swapping these 2. Just so you can check to see if the cans are different. Ready? 3, 2, 1. Wow, again, the one that was on the curved ramp hit the bottom first. Well, that's because of gravity. This slope is a lot steeper than this slope. So you can see it goes vroom, vroom, really fast at the beginning. Whereas this one kind of doesn't speed up as much. Because if you think about it, have you ever been on a bike with a really steep ramp? Yeah, you go down really fast, whereas this one is not as steep. So because it went faster at the beginning, it wins the race. Now, before we move on to some pretty cool electricity demos, we're going to go back to vacuums. Josh has one quick thing he wants to show you guys. It's really cool.
You thought vacuums were done, but they're never done. They're all around us. Now, first, we're going to look at a classic balloon. I filled it with just a little bit of air, and you may be wondering, what am I about to do to this balloon? You're about to see. I put it inside of our vacuum chamber. I connect it to the pressure, and we're about to see something very interesting as I turn on the pressure. Notice how the balloon is getting bigger as it begins to fill the chamber. Look at that. And watch as I unhook this and let the pressure back in.
Wow, that's really cool, Josh. Thanks. Let's head over to electricity demos with Ashley.
Hi guys, we're going to check out some really cool stuff about electricity. Right here in front of me, we have a Jacobs ladder. The way this works, when I turn it on, these two wires are going to get really, really strongly charged. And the electricity wants to jump between them, but the wires are not connected. So it has to go through the air, which is why we can see little arcs of electricity traveling up the ladder. Super cool. All right, now on to the next cool little thing here. I'm going to talk a little bit about static electricity. Now this is the same stuff as when you are walking across a carpet wearing some socks and you go over to touch a doorknob. That's what's happening between these two balls. It might be kind of hard for you to see, but I'm hoping you can hear the little crackle of electricity between them. Alrighty.
Looks like lightning.
Yeah. The electricity is just jumping between those two balls. It's got nowhere else to go, and it wants to be dissipated. All right. Now we're going to do a demo where we're going to take this empty can of Pepsi, and I'm going to put a little bit of water in it so that we know when it's heated up. And I'm going to set this can on this really hot plate here. You can see some of the water starting to steam up. And that's because heat likes to get these molecules of water really excited and wants to move around and spread out. The same thing that is happening with the air inside the can. It wants to get hotter, and as it gets hotter, it's spreading out and expanding. And we're waiting for it to heat up. And then I'm going to take this can and put it into this vat of ice water. And all of that heat that was inside the can is going to have to become really cold really fast. And we'll see what happens. All right, I think that's probably good. Oh, we're going to try again. Sorry, guys. Probably not quite hot enough yet. Take this time to get comfortable, enjoy this fun pre-Halloween evening.
And then just so everybody knows, this live stream will be recorded and posted on our YouTube video later, or YouTube channel later today. So if you need to use the restroom, grab some food, or you just want to check it out later, we will definitely be posting it so you guys can check it out later.
Great. Okay. We're gonna round 2. Let's try this again. Try to be faster this time. Okay. There we go. And it just crumpled. And that's because all of the hot air that was in there, when I dunked it in the water, it all had to become more compact all of a sudden, and it had nowhere else to go. So that actually brought the sides of the can in and made it all crumpled up. And I didn't have to apply any pressure to create that crumple. So yeah, that's how the can crumpling demo works. And we're gonna move on to the next one.
Alrighty, hi guys. So what we have here are two phone books whose pages are like interlaced. And the fun fact is that there is no glue, there's no tape, there's nothing holding these phone books together except the fact that their pages are put together. And what's really cool about this is that no matter how hard you pull or push on these phone books, they're not going to come apart. So even, hey, Josh, will you help me? Yeah, so if you take both sides and pull really hard, they're not going to come apart at all, right? See?
Well, how strong is it really?
We have no idea. So do you think it will fall if I sit on it? It's just paper. Do you think it'll hold me?
I don't know, that's spooky.
Let's find out. So if I sit on our little thing, I'm actually perfectly fine because, well, thanks, Alex.
The phone book is stronger than this even metal object itself.
It's crazy. And the reason this is because the friction between the pages makes the pages stick together. So you can't pull them apart. Yeah, and this was an episode on Mythbusters actually, also. And they actually had 2 tanks, like big metal tanks pulling, and even those couldn't get the phone books apart. This really shows like the magic of friction and some cool physics. So on to our next demo with Alex.
Hey everybody. So now we're going to switch gears a little bit. We're going to talk about sound. So sound essentially is a bunch of compression waves traveling through the atmosphere and basically hitting your eardrums and making it vibrate. Now, how can we show for sure that sound is made up of waves that actually push things? Well, we can actually, we can turn it up really, really loud, and we can slow it very, very much down, just so it's about 50 hertz or so. So as you can see, this right here is cornstarch in water. So essentially it's a non-Newtonian substance that you guys have probably heard a lot about. When you hit it very hard with, say, like a sound wave, it solidifies, but then when you don't hit it very hard, it turns into a liquid. So what happens if we play a specific range of frequency? There we go. Actually start to get it to dance. So it turns into a liquid again. Right. There we go. Look at that. So why do some frequencies work better than others? Well, we need to get what's called a resonant frequency, which means that the frequency, every time it bumps up against that cornstarch, we want it to get it a little bit higher and a little bit higher. But if this frequency isn't perfect, if it isn't spot on, then it doesn't really build it as much. We want what's called constructive wave interference, which just means it builds it up higher and higher as we keep putting in the sound waves in there. So next, we're going to go over and we're going to be talking about air, basically, other waves that you can travel through the air. Stand by. Stand by. On. All right, try to turn it on.
Let's go ahead and move on over to the optics table. And we will go ahead and do some stuff over there while we're waiting for the fog machine to heat back up. So over here, you have a bunch of different things that you can do with light, right? So this right here is a laser. And using only this laser, you can tell that right now, these things aren't spinning at all. So I'm just going to keep that on there for a little bit while we do some of the other demos. But as you can see, it's starting to spin using nothing at all other than the light bouncing off of it. But then if we take something like a mirror, right? As you should be able to probably see the camera behind it. To take this, you can then reflect it off of this onto whatever surface you want, which means that we should be able to get it back on this to keep it spinning. Because the light bounces off of surfaces that it hits to go to different places. If you then get something like this, right, you can see through it. But if you take light and you hit it through this, you can see that it interacts both right there and on the other side of it, right about there. And so there's a whole bunch of different things that you can do, right? You can also get things like this, which is a whole bunch of different lines in a very clear piece of paper. And when you look through it, it changes the way that lights look. So, and then you want to point it up a bit, can you see something?
Wow. See all the rainbows? How is that working exactly? Well, actually, it's taking the light, and like he was saying, it hits all those lines, and it's actually splitting the light. So what you normally see is actually a form of white light, just from like the sun, for example, and it can be split into many different colors. And that's exactly what these things are here. These are color filters. So this filters out light to make it so you can only see through green. Here, this one is a black color filter. And then we also have this one, which is the same thing as the diffraction lens, but it's just much larger. You can filter out different kinds of light, and you can see different colors. And then finally, we have these things. These are called polarizers. If you guys have ever heard about like sunglasses that are polarized, what I can do is you can see that half of the light goes through here, and you can also see that half of the light goes through here. But what I can do is I can pull them together and you can still slightly see me, right? Well, if I take this one in the back and just turn it slightly, it actually blocks all of the light. That's what a polarizer does. It blocks out certain types of light. Cool. So that's a little bit about our optics demos. Optics means light, so study of light. And we also have cool things like lenses that do different things. If you've ever seen like a fisheye, you can do lots of cool things with light. So now let's move back to the fog machine air cannon, which is one of my favorites.
All right. So as you can see, this right here is a little container with a plastic bag on the in the back and a circle, right? So what we're gonna do is we're gonna take this and we're gonna fill it with some smoke from the smoke machine. Alrighty. As you can see, there's a lot of smoke coming out right now. But when you close the bag, right, it takes the air and it shoots it out. And if you look over this way, you'll see that it forms little circles. But this doesn't just work with small objects too. If you get a bigger, still warming up. It's warming up again. So while we're waiting for this big canister to fill up with a whole bunch of smoke, let's go ahead and move on to some of our next demos. So these right here are just a regular old string of beads, right? But we put them in one of these cups. And so when we take these out, something really interesting is going to happen. And I'll show you this first one first, and then I'm going to go all the way up there to show you the next part. So if I just start and pull on it, right? Pop up. And it all falls out completely naturally. And that's because as that falls, it pulls out the chain faster than the cup can hold on to it, right? So it just launches it into the air. So now if you do a big one like this, up here, just the same old chain. It launches the chain out of the cup that it holds. This kind of works a little bit like a bendy straw, right? If you bend the straw and you drink out of it, it brings the water up and then it drops it down. If you keep sucking and the water falls, sometimes the water will keep falling and taking the water out. This is a similar concept because it's falling, right? The stuff that's falling is falling so fast that it even takes the stuff in the cup up and lifts it up in the air, so it makes it fall even faster. Now we're filling up the smoke machine one last time so you guys can see a giant cloud of smoke. I want to take a look that way. Right? And so if you remember what we were talking about earlier, this is just a really big container with a bag on the end. And since we cut out a little circle into it, or since we cut out a big circle into it right here, when we launch the smoke out, it comes out through there, making a circle in the air. And now we're going to be moving on to the grand finale, which is this bed of nails. So this right here is a regular bed of nails. But here we have a regular balloon. Normally, if you just take a balloon and put it on one of these ends, it pops. But you take a balloon and you place it here on the middle, you can push down on the balloon and it won't pop. So now we're going to do the exact same thing. We have a big bed of nails right here. And our very own plague doctor, apparently, is going to lay down and take one for the team. Need help getting down?
Yep. I thought human experimentation was banned by the Geneva Convention.
I mean, it was, but you're a plague doctor.
Ooh. How many nails are you laying on?
A lot.
All right. So this right here is a very heavy hammer. Ready? Okay. Hold on to this.
Oh no.
Right?
Don't hit my head.
I certainly won't.
3, 2, 1. Oh wow.
And as you can see, he's perfectly fine.
That was spooky.
Real spooky.
And remember, all of this stuff is science, right? And while we recommend if you ever want to do something like this, to do it around adult supervision, this is stuff that you can all learn if you go more into the science fields, in particular, physics. So ask your teachers about it, see what if you can do some of these demos in class, and I'm sure they'll be more than happy to help you. So, does our SPS team have anything else to say?
Yes, so we want to thank you all for coming. Again, just as a reminder, this whole video or live stream will be posted on our YouTube channel later today, so you can check it out later. Just as a final little thank you, we wanted to show you guys one of our cool new things we got in this building. So this, again, we are the Society of Physics Students at the Colorado School of Mines. And we all here, or most of us at least, major in physics. And physics is a very wide science field, and there's a lot of cool things that you can do. So anything else anyone else has to add?
Thank you for coming
Yeah,
by.
thank you for coming. Hope you enjoyed our haunted physics lab today. Thanks, guys.
Physics, right hand rule.
We did it.